They are capturing photons racing through space, measuring their energies, and pinpointing their sources. An army of high-tech telescopes, including Hubble in space, is reeling in enormous volumes of data that scientists use within models to explain how galaxies took shape. How stars live and die, and how the universe set the stage for life. What are we learning about the origins of our world and ourselves? In this age of Hubble. A brilliance to space that simply doesn't exist on Earth, wrote the astronaut Gus Grissom. Nowhere else can you realize so fully the majesty of our Earth and be so awed at the thought that it's only one of untold thousands of planets. For astronauts and stargazers, the universe beckons us to explore and to wonder. How did it all come about? And how do we fit in? Are there other worlds like our own, rich with life? Today, these questions are being raised anew by bold advances in the science of astronomy. The Hubble Space Telescope was launched in the year 1990 to capture the pristine light of distant space. It led a fleet of space-based telescopes sent up to probe distant galaxies, stars, black holes. By the time the light of these objects reaches us, it has traveled millions or even billions of years. It carries with it information about the distant past and how stars, galaxies, and the universe came to be what they are. Sending telescopes into space was part of a larger technological revolution. On mountaintops around the world, scientists began building a new generation of giant telescopes. To the powerful light-gathering abilities of precision mirrors, they added computer programs and sophisticated optics designed to cancel out distortions in starlight caused by turbulence in our atmosphere. The purpose? To gain the clarity of space here on Earth. Scientists have now opened another new window onto the universe. Supercomputer programs designed to probe the forces that drive cosmic history. These virtual telescopes are allowing them to literally set the universe in motion. To test theories about how the structure of the universe evolved on the largest scales. and how objects ranging from galaxies to stars and black holes form and interact. Perhaps the most important revelation in this age of Hubble is our own deepening sense of place within this immense universe. The ancient Greeks saw the heavens as a dome enveloping the earth that harbored the realm of the gods. The stars, they believed, were a pristine substance not found on Earth. Scientists would learn that Earth is not the center of creation, but rather one of 9 planets in a solar system. A galaxy. And a universe whose limits we can scarcely comprehend. We have learned that we are a product of the universe, part of a great cosmic continuum that reaches back to the beginning of time. That story begins with the earliest generation of galaxies and stars, at a time when the universe was awash in hydrogen gas. As the first stars formed, they began generating oxygen and carbon. Some exploded, generating heavier elements like iron or gold or magnesium. While spreading these elements far and wide in the form of dust. This computer simulation shows the evolution of a cosmic patch, beginning just 12 million years after time zero. The luminous matter in stars acts as a tracer for dark and ordinary matter, as gravity draws them into filaments, like a vast spider's web. Within the volume of this simulation, tens of thousands of galaxies take shape all along the strands of the cosmic web. Where the filaments intersect, something happens that will affect the character of every galaxy, star, and planet. Gigantic bubbles of hot gas begin to expand outward. They form when matter flows into large central galaxies and gets blasted out by supermassive black holes lurking in their cores. In time, these hot bubbles push out well beyond the central galaxies. The bubbles spread huge volumes of gas and dust created in earlier generations of stars. The bright central region of the famous Pinwheel Galaxy is surrounded by dark, dusty lanes. In spiral galaxies, the most common type, hot winds from exploding stars helped push these clouds toward the periphery, as well as above and below their flat disks. You can see evidence of this in our view into the disk of the Milky Way galaxy. Dark dust lanes and ominous clouds dominate our view into the disk, while tendrils of dust reach far above it. Here, above the plane of the galaxy, just 400 light-years from Earth, is a dense, irregular cloud of dust called Lupus 4. Our Sun, our solar system, likely formed in a cloud like this. Lupus 4 may one day give rise to a star cluster like NGC 3590, a region of dust and glowing gas near the plane of the galaxy. These young stars were probably all born at the same time, within the same cloud. The manufacture and spread of dust is an ongoing process in our galaxy. Consider the Crab Nebula. From a supernova spotted by Chinese observers in the year 1054 AD. The blast is still growing at a rate of 1,000 kilometers a second. Within the crab, there is enough dust stocked with carbon and silicate compounds to make some 30 to 40,000 Earths. The Carina Nebula is even larger. Located 7,500 light-years away, it spans some 250 light-years across. At its center is the giant star Eta Carinae, one of the largest and most unstable stars known in our galaxy. It is surrounded by an expanding bipolar cloud of dust and gas, known as the homunculus, or little man in Latin. Astronomers believe it was expelled during what they call the Great Eruption in the years 1838 to 1845. With a mass over 100 times that of our Sun, this star could explode at any time. And yet, in the larger cloud of dust and gas, stars are being born at a fever pitch. Here, a pillar of dust is being eroded by a torrent of ultraviolet light from hot, massive stars nearby. A dense region at the top resists these scouring winds, giving a young star time to incubate. Gas and dust flowing into the star are being blasted out in jets coming from its poles. Of all the constellations, few attract more admirers than Orion. Within it is a stargazer's dream. The Great Orion Nebula. A luminous castle of gas and dust, 1,300 light-years away. It's roughly the size of a full moon on the sky. At its heart is a star cluster called the trapezium, a brilliant formation first discovered by Galileo. It pumps out a wind of ultraviolet radiation that causes the surrounding region to glow. These large stars emit streams of charged particles that collide with dust clouds, forming a frothy landscape of arcs and bubbles. These winds are also disrupting the growth of hundreds of solar systems in the making. Despite these winds, some solar systems still manage to come to life. Using the Hubble Space Telescope, scientists have been drawing them out of their bright and hazy surroundings. Thousands of solar systems are being born in and around the Orion Nebula, in a rich chemical soup provided by large exploding stars. Amid all the dust, scientists have detected huge volumes of water. Where does it come from? And how does it form? In some cases, water is the byproduct of a star's death. When a medium-sized star like our Sun uses up the hydrogen in its core, it becomes unstable, shedding its outer layers. The Helix Nebula is a star that has puffed out into a colorful ring of glowing gas and dust. A tiny remnant of the original star, called a white dwarf, scours the ring with harsh ultraviolet light that destroys particular compounds, including carbon monoxide. The oxygen that's set free combines with hydrogen in a molecule that forms water. Dying stars are not the only source of water. "750 light-years from Earth, a protostar called L1448mm is shooting matter out in high-speed jets containing oxygen and hydrogen. When these molecules reach a cooler environment, they form water at a rate 100 million times the flow of the Amazon River. Water then becomes part of the dynamic of a solar system's birth. Scientists have sought to better understand the formation of planets by simulating it in a supercomputer. Gravity causes a central region to collapse and dust and gas to flow in. It forms a disk that swirls around the newborn star. Along the way, water acts like a glue, allowing dust grains to form larger bodies, from rocks to comets, asteroids, and finally planets. Up on the high deserts of Chile, astronomers have been using the Atacama Large Millimeter Submillimeter Telescope Array to peer into the turbulent environments of newly born stars. One of them, 450 light-years away, is known as HL Tauri. The star is no more than 1,000,000 years old, but there are signs that planet formation is already underway. Its hot core is cocooned in a cloud of gas and dust, the solar nebula. As matter flowed into the star, it has settled into a protoplanetary disk. This disk has a series of telltale grooves where the gravity of planets has begun to sweep up the dust. Dust within the solar nebula carries all the material needed to build a planet like ours, including organic compounds. So, how did Earth get its water? As the Sun vents heat from nuclear burning in its core, it generates a steady wind of protons that reach to the edges of the solar system. This wind encounters dust particles that are wafting through the solar system, attracted by the gravity of planets like Earth. When the solar protons interact with oxygen and silicate mineral grains, they form the molecule H2O. It happens one grain at a time. As solar particles race through clouds of dust, or strafe the surface of solid bodies. It takes place in regions where stars are being born, where dust is prevalent and solar winds are fierce. This process may be responsible for water ice that has collected in the bottom of some lunar craters and is strewn about lunar landscapes. It may explain how comets and asteroids acquired stores of water that they brought to our planet. Given that water is created and spread so readily, it's not surprising that it pervades our solar system. Within the folds of Saturn's rings are countless particles of ice. Hovering just above them is the moon Enceladus, with an icy surface that makes it one of the brightest objects in the entire solar system. Then there's Earth, a water planet. Vast interconnected bodies of water, the oceans, cover 71% of its surface. And now, scientists have detected whole oceans hidden in rocks deep inside the planet. The story of dust and water is central to our understanding of how life can arise. These two components can be found throughout the galaxy. But does life inevitably follow? For now, Earth remains our only data point. Among the thousands, even billions of habitable worlds that may be out there. So we lock our gaze on the heavens, searching for clues that explain how it all fits together, where we came from, and what the stars may tell us of our place in the spread of time and space. For astronauts and other stargazers, there is both a sense of wonder and connection as we unravel the secrets of creation emblazoned on the night sky.